Hello there. In this video, we'll be talking about continuity at a point. First, note that continuity in math refers to an unbroken curve or a curve that has no gaps, breaks, or holes. In this video, we'll be focusing specifically on continuity at a point. Now, there are three conditions that must be met in order to say that a function is continuous at a point. First, f is defined at x equals a, or this means that f of a exists. Second, the limit of f of x as x approaches a exists. And third, these two are equal. So, these are the three conditions that we must remember in checking if a certain point or a certain function is continuous at that given point. Now, it's kind of hard to understand how this works without a visual representation. So let's try to visualize what happens in here. So for the first condition, f is defined at x equals a. This means that there is a point wherein its x component is a and its y component is f of a. So this point exists. Aside from this, if the limit exists, then we know that the limit from the left is equal to the limit from the right in a graph. Unfortunately, for this second condition, this doesn't assure us that there is a point in that specific area. We just know that from the left and the right, it converges towards that point. But by the third condition, this means that this point fills in this one, like this. So, given these three conditions, we are sure that the graph is continuous. There is no cuts. It's not broken, there is no gaps, there are no holes at that specific point. So that is how continuity at a point works. Now let's move this one and take note that if at least one condition here isn't satisfied, then we say that f is discontinuous at x equals a, or at that given point. Since if one of these conditions isn't satisfied, then we aren't sure that the curve goes like this, or it's straight, no curves and such, or no gaps rather. So take note of these three conditions, since this is what we'll be using in determining if a given function is continuous at a given point. So to do this, let's have some examples, starting with the first example. So in here, we're given the function x squared plus 2x plus 3, and we check if it is continuous at the point x equals 0. Before we show how to do this, feel free to pause the video so that you may try this one first on your own. Okay, good. So let's start. So to show that, or to check rather, if this function is continuous at x equals 0, we'll just be using the three conditions that we had earlier, which I'll probably refer in this video as the 3-step test in continuity. So for the first step, we check if f of 0 is defined, or that is f of 0 out here. This is equal to, we just plug in 0 out here, so we have 0 squared plus 2 times 0 plus 3, and then this is just 0, so this would cancel. So is this one, since 2 times 0 is just 0. And so we'll just be left with 3. So we know that f of 0 is equal to 3 and it is defined and it exists. Next, we check if the limit of f of x as x approaches 0 exists. Yeah, exists. Take note that in evaluating limits, since this is just a polynomial, we know that from a previous video, we can simply just plug in this one out here into this given function. So it would look something like the first one. So we have 0 squared plus 2 times 0 plus 3, and again, this one will just cancel out, so we'll be left with 3. Now, since these two are equal, then for the third condition, clearly, f of 0 is equal to the limit of f of x as x approaches 0. So the three conditions are satisfied. And so, since these three are satisfied, we say that f is continuous at x equals 0. So we have found the continuity of the given function at this given point. And indeed, if we check out its graph, you can clearly see this is the graph of f of x. And at this point, at x equals 0, it's around here, it's just not seen. Clearly, the function is continuous out here, since this one is the part of f of 0, and then the function or the limit goes there. So this point, x equals 0, is indeed valid or continuous, or the function is continuous indeed at the point x equals 0. So I hope you got that one correctly, and as a remark, take note that in general, polynomials are continuous at any point a, since the domain of polynomials is just all real numbers, so we won't have any problems with that. So good, so let's move on to the next example. In here, we are given the function x squared minus 3x plus 2 over x minus 1, and we check its continuity at x equals 1. So this one now is a rational function, and before we solve this one, again, feel free to pause the video so that you may try this one on your own. Okay, good. So let's try this one out. Again, starting with the first step, we check if f of 1 exists, or that is, f is defined at x equals 1. So we just plug in 1 in this function. So we have 1 squared minus 3 times 1 plus 2 all over 1 minus 1. So clearly the denominator becomes 0. For the numerator, this just becomes 1. 3 times 1 is 3 plus 2, and adding these would give us 0. So we'll have 0 over 0, and since we are dealing with the value of a function and not its limit, then we know that this one is indeed undefined. So f of 1 doesn't exist. So we can actually stop here already, since the first condition isn't satisfied already. But for the sake of discussion, let's try to check out the other steps. For the second step, we have the limit of f of x as x approaches 1. We check if this one exists. So take note that we can write f of x out here as the given function. And we know that since if we plug in 1 out here, we'll have 0 over 0. So this one is an indeterminate in terms of limits. So we can try to apply factoring method in limits. That is, we factor this one. So take note that upon factorization, this is equal to x minus 2 times x minus 1 all over x minus 1. Then we can divide the x minus 1, since we are only dealing with values approaching 1 and not exactly at 1 itself. So we can divide that since x is not equal to 1, or that is x minus 1 is not equal to 0. And so we'll be left with x minus 2. Now we can plug in 1 out here without any problems. So we'll have 1 minus 2, and that is equal to negative 1. And so the limit of f of x as x approaches 1 exists, and it is given by negative 1. But again, clearly, the value of f at 1 is undefined, so it is not equal to the limit. So clearly, these two aren't equal. And so we say that f is discontinuous at x equals 1. Indeed, if we check out its graph, as you can see, there's a hollow point out here at the point 1, negative 1. Since again, the given rational function is undefined at x equals 1. So I hope you got that one correctly, and take note that as a remark, rational functions are continuous at every point except at the point that would make the denominator 0, since this point that would make the denominator 0 is a point that is not part of its domain. In this case, that is x minus 1 equals 0, that will be x equals 1. That is why we had a discontinuity at x equals 1. But if you check at the other points, like at this point, at this point, at this point, clearly the given function based on its graph is continuous at it. So that is how the polynomial and rational functions work in terms of their continuity at a point. So now let's move on to our last example. In here, we are given f of x equals the piecewise function x squared minus 3x plus 2 all over x minus 1 if x is not equal to 1, and 0 if x is equal to 1. So again, feel free to pause the video so that you may try this one first on your own. Okay, good. So let's try this one out. And so again, we just do the 3-step test. So starting with the first step. So we know that at f of 1, the value would be this one out here, since that is at x equals 1, it is given, or it is equal to 0. So we have this. For the next one, the limit of f of x as x approaches 1. Now take note that since we're dealing with values approaching 1 and not exactly at 1, we use this one, or this function. Take note that this one is actually, this is the same function in example 2. So you can refer to that one. So that's just the previous example. And take note that in the previous example, we found that the limit of this function as x approaches 1 is equal to negative 1, if I'm not mistaken. So we'll have this. So clearly, even though the function is defined at x equals 1, it is given by 0, and the limit exists, these two aren't equal. So we say that f of 1 is not equal to the limit of f of x as x approaches 1. So in here, condition 1 is satisfied, condition 2 is satisfied as well, but condition 3 isn't satisfied. So we conclude that if at least one condition isn't satisfied, we say that f is discontinuous at that given point, which in this case is x equals 1. So indeed, if we check out its graph, we can see that, so this is just the same graph as a while ago, but at x equals 1, so it's this one, the given point or its value is at the point 1, 0 because of this one. So indeed, even though this one exists and the limit exists, since this one is not out here, then we still have a discontinuity. But a good question to ask is, what if we replace 0 with negative 1? Or what I mean by 0 is this one. So if we replace that by negative 1, then what happens is that this one becomes negative 1 already. And so this one becomes equal. And its graph will be given by this. So we have a continuous function now. Or we say that f is now continuous at x equals 1, since the limit goes to this point, and this point is defined. So, as you can see, this one is our function in the example 2, and we were able to redefine it. We were able to redefine it so in such a way that the given function now, together with this rational function, is now continuous. So, why is this important? Why is learning about redefinability important? Well, this tells us something about the type. I hope this one can be seen. This tells us something about the type of discontinuity of a function. Since we know that in the first place, this given function is discontinuous at x equals 1. But upon certain adjustments, by having this part, we were able to make it continuous now. So this is something that is nice to think about, and actually this is something that we'll be focusing on in the next video. That is, we'll be discussing more on the type of discontinuity. As a preview, we have the removable discontinuity as well as the essential discontinuity. So, yeah, that's it for this example, and that's it for this lesson. But to formally end this, here is an exercise that you can work on. So determine if g of x is equal to this piecewise function 1 over x if x is less than or equal to 2, and 3 over 8 minus x if x is greater than 2 is continuous at x equals 2. So this is a nice exercise for you to try, since again we have a piecewise function here, but we don't know if this one is continuous or it's just discontinuous. So this is a nice example to try out for yourself. So yeah, that's it. I hope you enjoyed and learned a lot from this one. Feel free to comment down below if you have any comments, suggestions, and recommendations for this video and the channel in general, as well as if you have a solution and answer to this exercise that we have. So yeah, that's it, and that is all for this video.